Welcome to Module 3.5. In our last session, we looked at the balance sheet of the column, calculating exactly how many plates we have and what our ROI looks like. But a balance sheet only tells you where you stand at a single point in time. Today, we move into the operations phase. We are looking at the ultimate efficiency dilemma, the tug-of-war between how fast we can run our lab and how clear our data needs to be. Many believe that if you want speed, you must sacrifice resolution. I'm here to prove them wrong. Today, we master the Deemter model, your license to cut run times in half while keeping your peaks sharper than ever. Let's dive in. Imagine you're managing a delivery service. You have a rocket that hits 200 miles per hour but has zero suspension, or a luxury sedan that is perfectly stable but only goes 15 miles per hour. In the mass spec lab, we face this daily. We have a massive sample queue. We want speed. But we need to detect attograms of analytes. We need resolution. Most analysts stall because they don't understand the relationship between the pump, the column, and the mobile phase velocity. Today, we become optimization strategists. We're going to find that specific point on the curve where you get Formula One speed with luxury sedan stability. To master this tug-of-war, we need a map. Our agenda is built around the three consultants of rate theory, the A, B, and C terms. First, we'll define the A term, eddy diffusion, and why some molecules take the scenic route. Second, we'll look at the B term, longitudinal diffusion, the penalty you pay for being too slow. Third, we'll tackle the C term, the resistance to mass transfer, which is the high-speed resistance that kills resolution. Finally, we'll locate U-opt, the optimal flow rate, and see how UHPLC allows us to flatten the curve for maximum efficiency. In our last module, we established that N equals L divided by H. To make N as high as possible, our objective is to make H, the plate height, as small as possible. The Deemter equation is essentially the profit and loss statement of your separation. It is written as H equals A plus B divided by U plus C times U. Here, U is our linear velocity, the speed of the mobile phase. This is the primary lever we can pull. By changing U, we change how much the B and C terms contribute to our total loss. Our goal is to find the minimum point on this plot. Before the details, let's look at the framework. In chromatography, efficiency killers are categorized into three terms. First is the A term, or eddy diffusion, which is about the multiple paths in the column maze. Second is the B term, or longitudinal diffusion, which is about the drift that happens when molecules wander. Third is the C term, or mass transfer, representing the handshake, or the resistance molecules feel when moving between phases. Over the next few slides, we'll do a deep dive into each one to understand how to hack the system for better results. Think of the A term as people walking through a dense forest. Even if everyone walks at the same pace, some take straight paths, while others zigzag around trees. They all arrive at different times, because their total path lengths were different. In your column, this is eddy diffusion. Because packing material isn't perfectly uniform, some molecules find shortcuts, while others take the scenic route. The strategic insight here is that the A term is constant. It does not care how fast you run the pump. To win, we must make the paths more uniform by using smaller, more precisely spherical particles. Now let's talk about the slow and steady fallacy. Many think running the pump at a crawl gives the molecules more time to reach a better equilibrium. They are wrong. This is the B term, or longitudinal diffusion. Molecules naturally want to move from high to low concentration. If you move too slowly, the molecules spend too much time at rest and start spreading out sideways and backwards. In the equation, this is represented as B divided by U. As velocity goes down, plate height goes up. This is your low flow penalty. To beat it, keep the molecules moving so they don't have time to wander. Finally, we hit the C term, or resistance to mass transfer. This is the high-speed resistance. Imagine trying to have a deep business negotiation while running a full sprint. You won't have a productive exchange. In chromatography, we need the analyte to move back and forth between the mobile phase and stationary phase, the molecular handshake. If the flow rate, or U, is too high, the molecules move too fast to fully negotiate. The result? Your peak broadens because the exchange isn't efficient. This is the physical bottleneck that limits how fast we can go on traditional columns. So how do we find the sweet spot? We look for the optimal flow rate, denoted as U-opt. This is the bottom of the U on your Deemter plot, the point where H is at its absolute minimum. At this velocity, we have perfectly balanced the low flow penalty of the B term with the high speed resistance of the C term. If you run slower than U-opt, you waste time and lose resolution to diffusion. If you run much faster, you lose resolution to poor mass transfer. Our task is to find this point to ensure the highest possible efficiency. This slide shows the hack that separates masters from operators. Look at the difference between the curves. With standard 5-micron particles, the C-term upward slope is very aggressive. But look at UHPLC using sub-2-micron particles. The curve becomes much flatter and lower. Because the particles are so small, The distance a molecule travels for the handshake is drastically reduced, effectively killing the C-term bottleneck. This gives you the license to run at 8 times the speed and 3.4 times the sensitivity without losing resolution. Now for your performance audit. When you look at your next chromatogram, ask yourself, am I optimizing? If peaks are broad, which consultant is failing you? Is it the B term because you're running too slow? Or is it the C term because you're pushing a 5-micron column beyond its physical limits? A pro knows they can't just turn up the pump on an old column to save time. By using the Deemter model as your audit tool, you can justify every decision and prove your method is operating at the absolute peak of mathematical efficiency. Let's wrap up. Remember, plate height, or H, is the metric of success, and we want it as small as possible. The A term is about uniformity, the B term is the penalty for being too slow, and the C term is the resistance to speed. Here is my golden quote. Speed is a choice, but resolution is a requirement. The Deemter model gives you the license to have both. You are no longer just an operator. You are an optimization strategist. You know exactly which lever to pull to get results, while others are still guessing. We've mastered the physics of the race and the efficiency math. We know how fast to run and how to tune the engine. But one final piece of the puzzle remains. Now that we know how to run, how do we pick the perfect track for every molecule? Not every analyte wants to run on a C18 track. In our next unit, Module 3.6, The Strategist's Choice, we look at the decision-making matrix for choosing the perfect column chemistry. We'll match the analyte's personality to the column's soul. I'll see you there.